Swayam Prabha. Digital India. Educated India.
Good morning everyone. Welcome to the third day of this Gyan course on advanced manufacturing techniques and process monitoring. So today the first session will be on laser assisted surface texturing and its applications, and this part will be taken by Professor G.L. Samuel. Over to you, sir.
Yeah, good morning everyone. So we welcome you to the third day of the GIAN program on advanced manufacturing techniques and process monitoring. And so hope these lectures, the lab visits, the research park visits have been useful to you, giving a lot of technical inputs and the practical applications of various technologies. So today we are going to look at the topic laser assisted surface texturing and its applications. Now, when we look at the engineering components, the surface plays a very important role. And also, when you look at the surfaces, so their character actually plays a very important role in talking about or telling about the machine tool. And also, when you put these components to use, the surfaces which will come in contact or exposed, so they play a very important role. So, if you look at some of the textures or the surfaces which are being generated, we can easily identify their process. So now when you look at a component which is being turned, so we call it as a lay. So they leave the mark when you do a particular process. So turning means it is done with a single point cutting tool, and you can see these marks here. And similarly, if you are doing a milling process, so you can see the milling cutter which is circular, and then you will see those marks which have been left. So when it is grinding, which is done with the abrasive particles, so they actually rub the surface and you can see their marks here. And similarly, when you shape it or when you do the lapping and honing process, so you can see their marks which have been left on the workpieces. Now, what we are actually trying to do is that we wanted to control the surfaces. So now when you look at the surface which has been generated just by machining process, it is more random kind of a surface, and it is characteristic of the process by which you are making. But we find that in many of the modern applications, we don't want the randomly generated surface, but we want a specific, systematic, and repetitive kind of a surface. How do we do that? So that is what is called as the surface texturing. So we can do that by using this method which is called as surface texturing. So what is surface texturing? It is nothing but creation of precise and controlled surface textures on various materials. How do we carry out this process? So the surface texturing is also a process of generating these engineered surfaces that present with different features like micro holes, micro asperities, micro grooves, micro pillars, etc. That means we are going to make a specific shape on the surfaces, and that is called as the surface texturing. So here we can actually control the shape and size of these textures, and also the gap between them, the way how we need, so we'll be able to design it. Now when you look at a 3D surface, so this is the way how the 3D topography of the surface looks like. So we have different features here. So there are peaks, so where the surface is high, and there are valleys, so where it is going low. And then when we actually take the volume of these surfaces, so that is also actually important. And then we have the surface slopes. So they also play an important role. So now, for example, if the slopes are like this, when you incident a light ray, so now what happens is, because of this angle, the light gets scattered. Okay, so it doesn't get reflected into the, if you want to take an image, so it doesn't reflect into the device from where you are sending the light. So that is called as a light scattering. And then when you look at the volume of these valleys, so that plays an important role. So if it has more valleys, if you put a lubricant, so that lubricant can be actually in that valley, and it can contain that, and it will be useful. So that is the reason usually when you do the machining of the cylinder liners, so they use the process called as honing. So you have seen the picture in the previous slide. So it is honing. So that is the way how we have different characteristics of these surfaces. Now the main aim of texturing is not a random surface like this, but give a systematic surface so that we'll be able to get the properties which we are looking for. For example, if you want more lubricant to be contained in those valleys, you make the dimples, like a holes, dimples, and then space them in the appropriate way so that it can contain the lubricant. Or if you want the peak's height to be controlled, we can do that. So we can actually make what is called as a micro pillars, and then we can change the characteristic of the surface. Now, before we actually look into texturing and the surface characteristics, how they contribute to different properties, the first thing we need to know is, how do we measure that surface? I think in the first class itself, I have said that Lord Kelvin said, if you can't measure, you can't make it. If you can't measure, you cannot make it. So that means first we should know how we characterize these surfaces. Then only we'll be able to control the machining process and get the required surfaces. Okay, now what are the different measurement technologies which are there to measure these surfaces or to characterize these surfaces? So generally, initially, the whole process started with the stylus kind of a profile. So wherein there'll be a stylus which will touch the, will make the contact with the surface, and then they'll be able to tell what is the roughness. Hope you all know about the roughness, and there are various parameters by means of which you'll be able to quantify the surface finish. Okay, so the stylus is one of the instrument, and in fact, even earlier than stylus profilometers, actually our hand is the best sensor or a stylus. So they used to actually touch the surface, and then they used to compare it with a standard surface. So with the left hand, you touch the standard surface, with the right hand, you touch the machine surface, and then they used to say this is okay or not. It is whether it is within the range what we are requiring or not. So that's how our hand itself is a sensor, touch sensor. Okay, so from there, I think we moved on to the stylus profile. So then later, the more improved kind of a technologies have come. When we had stylus, mostly it was a line profile. But now, even actually we have an instrument, so where with the contact itself, we can do several scannings and get the 3D profile of the surface. So then after that, the white light scanning interferometries have come. So wherein we use the interference principle, then we'll get the fringes, and then we get the surface textures. So then we have a technology which is called phase shifting interferometry. That is also again based on interferometry, but we have shifting of the phase, and that is actually a good principle which has been used to get even a higher resolution in the height of these textures, sorry, in the surface profile. Then we also have SEM. SEM is nothing but scanning electron microscope. And also we have scanning probe microscope. So what we use is called AFM, atomic force microscope. So these are all the instruments which are there in our lab. So you can go and actually visit them. So that is the reason I wanted you to go and see these characterization devices right today after your lunch. So this is the surface roughness tester. So where you'll put the workpiece here and then there is a profile. So we have a stylus here where we can touch the stylus and then get the profile of the surface. But more advanced one. So we have actually in our metrology lab. So we have a 3D profiler, but contact based. And this device is a very, very delicate device. I think you need to handle it very carefully, right from the probe which has been used, so that stylus probe. So the diameter is just few micrometers, and then it need to be handled carefully. And this device, what it does is, it will not only take the 2D profile like this, but it will give us the 3D profile. So how it does that one is, so first with the contact, it will go here. So then it will go and then take the second line, then move to the next position, take the second line, third, like this. But this is very, very time consuming. So usually if you want to measure a big surface, so we can actually automatically load it, program it, and then leave it for many hours and then come back and we can see that the whole profile is obtained. And also there is a mechanism which is called as a stitching. We can actually take them in smaller parts and then stitch them together to get the complete profile. So then we have the non-contact based surface profiling instrument. So wherein this is called white light interferometry based device. And even here also we have the probe here. So we have different magnifications and then at what heights it can scan. So you can set them. So it will be like few micrometers. You can set how many scans it can take for a given depth. So usually what we do is first we take a rough measurement and then see what is the maximum depth, and we give like more depth than whatever is the maximum value. So thus it will make a scans, and then it will also stitch various profiles, because when you use a higher magnification, so the area what it can see will be something like 250 micrometers by 250 or 500 micrometers by 500 micrometers. But then when we need a higher surface, so we need to stitch all these together. So the software has a mechanism, actually there will be a percentage of overlap like 20 or 30%. So they have the feature, they match it, and finally they'll give us a profile what you are seeing here in the bottom side of the picture. So then we have the scanning electron microscope, so which has like 1 lakh, 2 lakhs kind of a magnification. So if you want to look at the nano textures or with a smaller features, so we have to go for the scanning electron microscopy. And do you know why these images will be black in color? Does anyone have any idea? So maybe some of you not have seen, but some of you might have used the same images. So why do they look black, like black and white images? But if you look through a microscope, so like a biological kind of a microscope, you can see the true colors. Okay, but in the previous slide, whatever I have shown, so these are not true colors, but these are the height representations. Okay, so these are the height representations, they are not the true colors. Only our biological microscopes, so where we see the true color, actually whatever the color is there, that we can see. Yeah. So any idea what is this image, why it should look like this?
Sir,
maybe here we use electron beams. Because of that, maybe we get black and white, since in microscopes they use visible light to capture those images.
Yeah, that's right. Okay, so in the optical microscope, so we use the optics and we use the white light, so we get the true colors. But here, they are the electrons which are reflected, and thus it's only black and white. And also, actually, there is an issue here. So we get the 2D image. So thus, sometimes it becomes very difficult actually to access what is the depth of the profile when you get the 2D image of the profiles. And also we have the confocal microscope. So this we have recently installed. So today you can look at that. So it is a very, very interesting principle. Probably you can look at the details when you visit the lab. So wherein we can get actually a nanometer kind of a height resolution. So thus you can see the picture what you are trying to take here. You can see the heights so clearly imaged. So thus the confocal microscopy is an interesting principle. So where there will be piezo actuators, and then at every time when the height changes, so the piezo actuators move the lenses to focus it, and then the moment how much it has moved, so that is what the information is used to reconstruct the actual profile. So thus we get a very, very clear images by using the confocal microscope. And also the atomic force microscope is another instrument which will be able to detect the heights. So here we can see the profile which we have obtained. So yesterday I think I mentioned that there are different methods by means of which we'll be able to get this reconstruct the actual profile. So it is contact type where the nano probe touches the surface, and then now when it is on this top the probe will move up, and then when it is here it will be moving down. So these up and down motions are captured, and then they are used for reconstruction of the surface like this. And also there is a method called non-contact type. So there will be a small gap between the surface and the probe, and then we know that there will be the repulsive or attractive forces. So based on that, so if the height is here, they repel up to this, but when it is here, this will come down. So like that, based on that information, the structure will be reconstructed. And then in some of the mechanisms, actually it will tap, and then we'll be able to get the actual profile. So these are some of the characteristics, how the instruments, how we'll be able to get the characteristics of the 3D profile of the surfaces. Then one more interesting property you need to understand before we go for texturing. So that is called as the contact angle. Okay, so the angle whatever you are seeing here, so that is called as the contact angle. So now when you have a surface and then put a droplet of water or any other liquid, so what is going to happen? Now if you take a maybe a tissue paper and then put water, so we see that immediately it absorbs. And then I have said already the example of a lotus leaf. So when you put the droplet on it, so it will just stand like this. So what is the difference between these surfaces and what makes it to behave like that? So now on a surface, so wherein when you put a droplet, if the angle is less than 10, so here this will be the angle, which is very small, we can't see. So this is called as, okay, hydrophilic surface. That means it absorbs water. Then hydrophilic, general hydrophilic surface is like the angle is less than 90 degrees. So commonly we find this. So getting a super hydrophilic is difficult, but in some cases we can get that. So these are the two common ones which are called hydrophilic and hydrophobic surfaces. So hydrophilic means it gets wet. Hydrophobic, so you would have heard this term phobia. Phobia means you are afraid. You don't want it. So thus here it don't want to get itself wet. So hydro is water. So thus when you put a droplet of water on the surface, so it doesn't wet and the angle will be greater than 90 degrees. And generally, if it is a super hydrophobic surface, so the contact angle will be more than 150 degrees. So in that case, we will be able to make the surface which will not get wet. Why we need that we are going to see little later. Now why I am telling this one is, now if there is a surface which is actually super hydrophilic or hydrophilic, but then if you want to make it as a hydrophobic or even super hydrophobic, we can do by using the texturing. So that is the reason these properties are important. We have actually a device that is called as a goniometer. So wherein we have the provision to put the drop of water on the surface, and then we have a camera, so which will actually capture the image, and then we can make the measurements and say whether it is hydrophobic or hydrophilic or even super hydrophobic or super hydrophilic. We'll be able to tell them. Now, coming back to the surface texturing. So the general term which has been used for this is called surface modifications. Okay, so surface texturing is one of that. Why these modifications are required and what are the different methods are? Like you have coatings, so where you can have a sputtering mechanism, or CVD and PVD. We can also have a chemical conversion, it's called passivation. So or we can give a chemical treatment, expose it to a gas, or put it in a bath of liquid, the surface characteristics changes. Or we can also have plasma treatment. And another important thing is that we can actually do the surface texturing. And why is that? So one of the reason I have already said that if you want to change the properties from hydrophilic to hydrophobic, we can do that, or the other way also is possible. And also we can actually improve these characteristics wherever there are two parts which are coming in contact. So there we can actually improve the tribological properties. So what are these tribological properties? Like friction, wear, lubrication, and other properties. See now, for example, you have a cylinder. So we have an IC engine. So wherein we have a cylinder and a piston. So now piston will be reciprocating and it will be at a very high speed. So generally the RPM will be like 6,000, 8,000, and sometimes even it goes to 10,000 RPM. So that means the piston will be reciprocating with a very high number of times in the cylinder. Now when the two surfaces come in contact, so friction plays an important role. So we need to actually decrease the friction, otherwise the engine actually gets heated up. So obviously we cannot make it zero. So we have the lubricants and other mechanism to decrease the friction. But what we are trying to tell here is that by texturing, we can actually decrease the friction. So we are going to show that. Then wear. So whenever there is a rubbing which is taking place, so there'll be a friction and then the surfaces actually gets worn out. Even that actually we can improve. So that means we can reduce the wear when you do the texturing. And then lubrication properties, as I have been telling. So now if you make a dimple, that means, sorry. So if you make a surface with these kind of a dimples, okay, so the picture is not that clear, but fine. So the lubricant actually can be contained here. So these depths will be few micrometers or even nanometers. So the lubricant can be contained here, and then we get the better properties. So thus, by surface modifications, and that too by the method of texturing, so we can actually improve all these tribological properties. And there are other benefits also, like we can extend the component life, we can enhance the fuel efficiency in IC engines, or we can prevent the corrosion and even icing on the like aircraft wings and other surfaces which are exposed to low temperatures, and then we can even reduce the waste. Now, how do you make these surfaces? How do you make these surfaces? And mostly we have in the nature several interesting surfaces. So one example which always we have been mentioning is the lotus leaf. And similarly, you can see that fish are there, or even the sharks and these things always in water. So you take any component or any part and put it in water, you know what happens? After a few days, you find that the algae and the fungus grows on it, and then it becomes slippery, and the whole thing deteriorates. But the fishes and sharks and all these things are always there, but they don't get that kind of things. And also when you see the way they move in water, so it is quite fast. They'll be swim very fast. That means the friction should be less, otherwise they can't swim that fast. So how are these able to get these kind of properties? And one more interesting property, so which I think nowadays we have been using it in the operation theaters. So the walls, if we look at the walls after rain, you know, you see a black marks there. You know why? The because of the moisture, the fungus grows, and then when it is exposed to sunlight, it gets dried up. So sometimes it looks green, that means it is still alive, or when it dries up, it becomes black, and all the walls get that kind of things. But now in an operation theater, we don't want those fungus or algae or bacteria to be there. How do we make that kind of a surface? So again, we can get the inspiration from the nature, and we'll be able to do that. Another interesting thing is even the swimming suit. So like in the Olympics and other games, so even a fraction of a second actually matters. So thus, if the body resistance can be decreased, so we can see that they can move fast. So sometimes in the swimming, you'd have seen they'll wear even a full hands, full dress. So this kind of a swimsuit. Why? Because better than our body, so the swimsuit will give lesser resistance. Okay, so thus even gents also wear a full kind of a swimsuit. And examples of ships and even the aircrafts. So in all these places, it's important that we should have that kind of a texture, so which is there in the nature. So as already we have been talking about these characteristics, so of the lotus leaf, so this has the pillars, micro protrusions or micro pillars we can call like this. So then we can see that even there will be a small, if you touch them, I think you can feel that there'll be a nano waxy kind of a small protrusions. So wherein when you put the water here, so they actually stand like this, and then the contact angle is more than 90 degrees and even more than 150 degrees. So thus the water droplets actually just stay like this. And in the nature you can also see a lot of pillars like this, nano pillars. And nowadays actually we have the mechanisms to create them, uh, create such kind of textures which are called as the nano pillars. And also in self cleaning of glasses, so where if you tall buildings will not be able to clean, but we can make the texture in such a way that no dust actually sticks to it. And also like waterproof clothing we can make. So when you make that, you pour water, it doesn't stick. And also another application is in the glass mirrors or even the windshields of automobiles. So during the rainy season, so we'll see that they doesn't actually get wet. So these are all the applications when you make the textures on the surfaces. So even some of the engineering applications, so we can make these grooves and get the characteristic surfaces as we need. And also some of the components like the piston rings, bearings, so where always friction is a matter, so there we can decrease them. Later actually one of our PhD student worked on this topic, so we are going to see some of the results toward the end of this presentation. Yeah, how do we make these texturing? So we have already actually been talking about our laser facilities. So we can do it actually with different types of lasers, but femtosecond, as I said, it gives a very precise control, and thus we can actually produce a beautiful controlled surfaces. That means beautifully textured surfaces. So I think we have already talked about the mechanism, how it works in the previous class. So here are some of the textures which have been made. I think one of the participants asked a question. So if you want to get a geometric shape, how do we do that? So by using the software, actually we can make any geometry what we need, and then we can produce them. So here, if you start putting more pulses here, the material will get cut. But here we are trying to control the depth of the texture. So it will be only one pass, it will go. So always deciding the parameters for the laser is important. So how many pulses per second? So what is the frequency of pulses? So that will be generally told in like hertz. What should be the pulse energy? So do you want to give the full energy or control it? And what is the scanning speed? So how fast will be moving? So all these things actually plays a very important role, and if you can control them, so you can get the textures, a beautiful controlled surfaces like this. So in the beginning, I have shown you one surface which is actually, that's a random surface, a 3D profile which I have shown. But here you can see that it is a specific kind of a texture we can get. So similarly, this is like the shark, fish kind of thing. So square, and you can have actually dimples, or even you can have the protrusions. So both we can actually do it. So like a fish scale kind of a textures, either protruding or it can be even like a dimples. So even circle. So here you can see that the circular one, but there might be slightly change in the diameter or the shape because of the process. But still, if you can optimize, if you can make a modeling of the energy and finally give just sufficient energy, so you'll be able to even get a better kind of these surfaces. Yeah, any questions till now?
So I have a doubt in surface texturing in marine applications, sir. So
Yeah.
while doing the surface texturing in ships, will it allow the growth of microorganisms in ship?
Yeah, that is the reason why. So if you have seen some of the old ships, in their parked, you can see that the algae, fungus, microorganisms will be growing on that, and then it also finally leads to corrosion and the life. The whole hull gets deteriorates. So to avoid that one, we need the texturing.
Okay, sir.
But there are a few challenges. See, actually, in our lab, and in the components for which we have made, they are all actually smaller surfaces. Okay, so that is the reason we can do the texturing directly by using the laser texturing on the surface. But if you think that you need a large surface, do you know how we can make that? Now with the laser, if you make, it takes hours together and it'll be very expensive and time consuming, but the size of the hull is very big, or if a sheet metal will be very large. Do you have any idea how we can scale it up like that?
While manufacturing the
Sheet
sheet
metal.
itself,
Yeah.
we have to do the surface texturing.
What is that?
So by manufacturing the material itself, we have to do the surface texturing.
How can we make it? Any idea? Yeah, while manufacturing, you need to do that, but how do we do that? Yeah, so as you said, it's right. For example, if you are rolling a sheet, and then if you want the texturing, so on the roller itself, you make the texturing. So if you want actually dimples on the sheet, so you make the pillars on the roller. So when it is rolling, so you make it. So thus they have a different ways how to scale up this. But here, all the experiments what we have conducted, it's on a lab scale and a smaller surfaces. So we directly use the laser. But now, if we want to scale it up on the roller, we can use these lasers and then texture it, and those rollers can be in turn used for producing it in the large scale. So thus even for the dies when you are making, so we can make the die surface textured. So then all the components which are made with the help of those dies will have the texturing. But only you have to make it negative. Yeah.
Okay, so one more doubt in
Yeah.
aerospace industries, defense area. Will the surface texturing reduce the RCS value of the aircraft's radar cross section?
Yeah. So what actually we can do is that we can make the angle in such a way that the slopes, as I have shown, no, in such a way that it doesn't reflect, but it should scatter the whatever light or waves which will come. If you can scatter them, you can actually make it non-detectable. Still a kind of a thing. So they use coatings and other mechanisms. So texturing is another way where it can scatter those waves.
Okay, thank you, sir.
Yeah. Yeah. So now we'll be looking at how do we texture the cutting tools to improve the tool life, to decrease the friction, and make it better for lubrication. So this work has actually been carried out by one of my PhD scholar, Dr. Niket, who has already completed. So we'll be looking at some of these things. So the previous textures which I have shown, so that was carried out by Chittaranjan, who is there with you now. So any doubts you can ask them during the afternoon lab visit. I think we all know about the cutting mechanism. So wherein when the materials or metals are being cut, so we have a tool here, then the workpiece. So then the depth of cut, the thickness of the chip, and all these things. So we have the shear angle, so the rake angles, the contact length. Actually, later it turns like this, and the chip will go away. So all these things actually are important. And then because there'll be a shear and contact taking place here, so we have the primary deformation zone, secondary deformation zone, and tertiary deformation zone. And at these places, the heat actually gets generated. So there'll be friction and then there'll be heat. So the metal is making the contact with the tool. So thus the friction plays an important role. And then when the friction is there, the heat gets generated. So which is actually not good for the tool life. And also if you are machining some of the materials like aluminum, so the built up edges will get formed. That means the material will soften and then gets welded to the tool. So that's called BUE, built up edges. And in drilling, even the process is more complicated. So we have actually a twist drill, they call it, because we have a helical shape. And then we have a chisel edge, chisel angle, and then the drill is going to move down and then drill it. So these surfaces makes contact. So now the main problem here is how do we decrease the friction? And the second problem is whenever you are drilling a deep hole, so we have to lubricate it. Otherwise, if the friction increases, then the tool gets stuck. So finally, it can even fail catastrophically. That means the drill bit can fail. How do we decrease it? So for doing that, so here we see basically two surfaces here. So this is called as the margin side. And then we have this surface, so which is called as a flute surface. So then we have the other surfaces which need to be textured to decrease the friction and then increase the lubrication. I have shown you the previous textures which was made on a plain surface, like a flat surface. But here the bigger challenge is that on this kind of a surface, you need to make the textures and on these surfaces. So how do we make, and then how we'll be able to reduce the friction? So these are the challenges. So why we are actually trying to do that is that, as we said, nowadays, the aerospace industry is one of the, like, a lot of demand is there, automobile and then space industries. So a lot of components and technology actually goes into that. So I think even yesterday when Professor Shreyas Melkot has been talking, so we have always been mentioning about the jet engine or aircrafts and all these things, because so those are the areas where a lot of technology is required. So now we have titanium alloys or even the nickel alloys, so which fall into a category called difficult to machine materials. Difficult to machine materials. So why? Because their conductivity is very low, they are light, have a structurally very strong, that is good, but at the same time they are thermally less conductive. So that means what happens is, as I have shown you the picture earlier, so the places when you are machining, wherever the contact is taking place, the heats get generated. And if it is a normal material, which is a very good conductor, heat actually get dissipated. Thus, the tool doesn't get much heated, and also the workpiece doesn't get much heated. Thus, that will be good. But here, it is not conducting, so the tip actually gets heated up, and then the built up edge also forms, and then the tool life actually decreases. It gets worn out easily, and the tool fails. So that is the reason these are called as the difficult to machine materials. So the machinability is very less. But now there are companies like aircraft manufacturing companies which have been spending a lot of money to develop the technologies to increase the machinability of these kind of materials. Now, how do we texture these surfaces? So for that, what we have done is we have conducted the initial experiments. So wherein to find out what should be the diameter of this dimple, and then what should be the spacing between each of these dimples, and also the space between these things. So all these parameters actually plays an important role, and also the depth, so which we are not able to see clearly here, but what should be the depth. So now we have conducted several experiments. So my scholar, Dr. Niket, has conducted several experiments here, and then we tried to characterize and see which is the best one. So thus, initially, so the texturing was made on a flat surfaces, and then the experiments were conducted, what is called as a pin on disc uh, experiments. So we are not actually going to take you to this facility, but if you need, we can arrange visit for you if somebody are interested actually to see this. So Professor Amitav Ghosh and also in metallurgy department, these facilities are there. So we can talk to them and arrange a visit if you are really interested. So what will happen is there'll be a disc, and then there'll be a pin with a different shapes. So like it can be a spherical shape or a flat one. So where we apply a particular pressure and then rotate the disc when this is making a contact, and then when continuously it is rotating, so there'll be a wear. So thus the pin and the disc combination you can make, like depending on what practically you want. So if there are two titanium uh, materials which are rubbing, so here you can make the plate and also the pin and the disc with the same material, and we can study the characteristics. So these experiments were carried out, and then when we see that, now whenever we put a texture, so we find that the friction coefficient, the coefficient of friction actually decreases. So here we see that this is a surface which is not textured. So it is a untextured surface, we can call it. And then the red color one shows the dimple surface, and then green color it shows the grooves. So now untextured surface actually the friction is higher, but when you do the texturing, so both the dimple or groove, so we can see that it decreases. But actually we found that dimples have a better characteristics. Sometimes there is a lot of variation in the texture with the grooves. So thus probably the dimple would be a much better option. So now when we have friction characteristics, so the adhesion and then bonding and all these issues will be there. So we need to control the coefficient of friction. So for the non-textured surfaces, so if this is the coefficient of friction, so for a micro dimpled one, so it has come down. So thus micro dimples is the best option for the texturing. So here we also see the variation of wear with the sliding time. So now we find that the friction in the plane surfaces, it goes like this, but with the textured one and the dimple one, so the wear depth actually is less. So as the time goes, so we find that the wear depth or whatever is the material which has been worn out, that will be significantly less when compared to the untextured surface. So thus friction is decreasing, so thus the wear is also reducing. As I said, now the challenge is that we need to texture the cylindrical tool, but then which is a spherical surface, and again we have the margin here. So where on the flute side and on the margin side we need to texture. So you can see in these figures, so the optimized dimples have been put on the helical side and also on the margin. So margin is this portion of it. So then later we have conducted the experiments on the machine tool, and then we have also recorded the cutting forces and the tool wear and other characteristics to see how it is actually really making an impact. So now when we make a test specimen and test it, obviously we see that there is an improvement in the characteristics. So the friction decreased and the wear decreased, but does it really happen when we use on the drill bit and when we drill? So that's what has been investigated. So these are the experiments, experimental setup which has been made. We also actually tried what is called as MQL lubrication. MQL means minimum quantity lubrication. So nowadays even SQL has come, small quantity lubrication. So generally we use what is called as a flood coolant. So where we pour the coolant during the machining operation, both in milling, turning, or even in drilling, we do that. But then later, people try to decrease the use of the lubricant and also not to cause harm to the environment. So people started looking at different types of lubrication and also to make it more efficient. So the MQL, minimum quantity lubrication, so which we have used. So what it does is actually the coolant will be pressurized and then it will be made to flow through a nozzle and then it will be focused directly at the uh, tool workpiece contact, so at this place. So that is one of the other method which we have been used to make the process more efficient, and within that we try to make the comparison. So usually 6 bar is the pressure which we have used, and then we'll use the nozzle and make the coolant to reach the tool workpiece contact. So then as the tool touches, then moves to the different depths. So what is going to happen for the cutting forces? So one of the cutting force here is the thrust force. So it will be acting in this Z direction. So now we see that initially when the cut is starting, so like this, so the friction actually, sorry, the cutting force actually increases very steeply because it was from zero, no contact. So now it has touched and then the thrust force increases. So then during the second stage, so we find that it increases but relatively slowly as a depth increases. Then there'll be a stable stage. Then after that, it again decreases. So now in that, when we tried with the different tools, so we can see how there was an improvement. So the first one is the non-textured tool. So the thrust forces were higher. Then the flute alone, if it is textured, so this is the one. Both margin, if it is textured, this one. But if flute and margin both are textured, so we see that there is a lot of improvement from, okay, even if you take an average, so from that to something like this. So this is the amount of decrease in the cutting forces. So the thrust force basically. So and also we have actually varied different parameters and compared. So we find similar kind of a trend. So where we can change the feed, speeds and other variations. So then torque is another important characteristic. So even that torque, so we find that with the non-textured, flute textured, margin textured, and flute and margin both textured. So we see that, so there is a significant decrease in the torque. So thrust force means acting in this direction. So torque means this is the force in this direction, so rotary direction. So also after varying feed and cutting speed, we see that in almost all the cases, so we find the texturing with both flute and margin side, so have an improvement. So then after conducting these cutting experiments, So we have actually looked at the surfaces. So what has happened to the tool surface? So when we observed, we could find that there are interesting things which have been happening. So in some places, we see that the whole dimple has been closed. And in other places, we see that the workpiece material, so where the debris got trapped into this. So that is actually a good one. And another interesting thing is that we'll not be able to use this tool infinitely because these kind of things happen. So wherein some of them get sealed after time and then they entrap. But if you can have a mechanism, so where they can be removed during the machining itself, that will be good. We can increase the even the life of these textures even to the higher extent. So thus they entrap them and that makes it better. Otherwise, what would have happened is these debris would have rubbed with the surface of the machine surface and then it would have spoiled actually the surface finish. So thus indirectly we are also getting actually a better surface finish by doing the texturing. So this is another view where you can clearly see that. And also we have carried out the EDS analysis to see what are the materials which got trapped, whether it is the tool material or it is the workpiece material. So it is the workpiece material, yeah. So we also see that, as I said, the built-up edge, is very crucial for the tool life. So once the built-up edge forms, so the tool angles actually vary. So these built-up edges will act as a pseudo cutting edges. So thus the dimensions are lost, dimensional accuracy is lost. So the surface finish gets spoiled. And then later what happens is after some time, so they chip off, they will come off. And then while it is coming off, it also actually removes some of the tool material. Okay. So thus tool wear also will be happening. So, but here we observed that with the non-textured tool, so that phenomena is very prominent, but with the textured tools, so that is very much decreased. That is because the temperature will be less and the friction and wear are less. So as I said, another challenge which we will be facing is the high aspect ratio holes, so depth. So again, if it is a non-textured tool, so we'll not be able to go much deeper and then the tool wear will be bad. But by using these kind of textures, we see that we can actually improve all the characteristics what we are looking at. And then even the burr formation. So whenever the drilled tool, when we have a through hole here, so actually the burrs will get formed and then they'll get stuck to the surface. But with the textured tools, so we find that we can have a better surface with decreased burrs. So here, this is the way how the burrs will look, but we can decrease them and avoid that if you are using the texturing. So you can see these kind of things which will be happening. Usually, even you go to a workshop, so you take a hole which has been drilled, and if there are materials like aluminum or even titanium, so this phenomena is very, very prominent. And we have also looked at the details of the burr and other analysis we have made. Yeah, any questions?
Sir, you mentioned that the burrs are formed very less in the textured tools. How the textured tools are making the burrs to form less, sir?
Yeah, actually, so now we have the temperature and all these components. So now when the material gets heated up, so the burrs will be formed. So thus, if we can control the temperature, then actually the less amount of burrs will be formed. So we can actually have one more detailed, one of my other student, Dr. Giridhar. So he has worked on machining of titanium, and he has looked even into more clearly. So while doing the machining, how the burrs are formed and why they get stuck, and then how we'll be able to decrease that. It's so basically the temperature plays a very, very important role. And also it forms like a cap. So thus if we can have a better machining, so that cap can be go out, and then that gives a better surface.
Yes, sir. One more doubt, sir.
Yeah.
You told that the debris will get entrapped in the dimples of the surface texture.
Yeah.
How to remove those debris, sir? Is there any strategy to like remove the debris?
Yeah, actually, we have a challenge here. So after you use the drilling tool for some time machining, so they get trapped. But we didn't actually try exactly to remove that. But what we can do is we can have a pressurized air, and then we try to clean it. But sometimes, so they get also welded. Okay, so they get welded, so it becomes a challenge. So we cannot have infinite life for these things. So now even on a plain surface, so when you make the dimples, so when they get worn out beyond its lifetime, so they will be actually gone. So you might have given a particular depth, but after it gets worn out, so that depth decreases.
Yes, sir. Like, how does the tool life compare with normal actual drill bits, sir? How it varies? Like, does it give a better tool life in terms of?
Yeah, obviously it gives a better tool life. Yes.
Fine, sir.
Yeah, so we'll move on to the last part of it. So actually, we have also carried out the work in ARCI Hyderabad. So Dr. Ravi Bate, and then one of my student Nazir Basha. So he has worked on texturing of the piston rings. So here also actually we tried different types of texturing, and then it was literally tested on an engine, and then we found significant improvement in the tribological properties. So generally, gray cast iron is used for the engines. So sometimes I think nowadays, even to make the automotive engines lighter, they started using aluminum alloys, but mostly the gray cast iron is being popularly used. So here we see that there is a carbon here. This is the carbon, and then iron here, and these carbon actually helps in the lubrication of, so carbon and graphite, so they help and they improve, they act like a solid lubricant. Okay, so thus we'll see later that by texturing we can actually expose more of this carbon. So thus not only the texture decreases the friction, but also exposing of this graphite or the carbon helps in decreasing the friction. So here also initially several experiments were conducted to find what will be the best kind of texturing which we need to do, and what should be the space, so that we can decrease the friction. So several similar kind of an experiments were conducted. So the textures were made with different parameters, and then we have tried all these things. And this is the image where you can see that when we do the cross hatching, so even the graphite actually, it's a very highly magnified. Okay, so this is with a lower magnification. When you go for even higher magnification, so this line is this is the kind of texture what we can see, and this is. So the interesting phenomena what you can see is that wherever the texturing is made, so there you can see the carbon actually flakes coming out, and that actually contributes to decrease in the friction. So I think there are several such kind of an experiments which have been conducted using the tribometer tests, and then to find out the variation of the coefficient of friction, and then the life and all these things similarly. And finally, we found that the micro dimples which are made were much better in improving the properties. So I think there are work we need to carry out similarly, as I said. So what should be the distance between each of these dimples and distances? So they have been finally optimized and then implemented in the piston rings. So we can see that when we have the non-textured surfaces, so the debris get stuck here, but when you have the textured one, so they go there until they are completely blocked. So up to that, it's fine. So these are the piston rings on which the textures were made. Sorry, there, and then finally it was put on the engine, and then it is implemented. So some of the information actually we have not given here, because I think he's about to submit the thesis. So that is the reason we have not given all the full details. But here we can find that so when you texture them, so we get actually better properties. So I think I'll be able to tell only that. So once all the thesis has been submitted and he gets the degree, probably we'll be able to give out more details. Yeah. Thank you. Thanks for your attention. Any questions?
So have you done the surface texturing in the cylinder sleeves of the engine?
Yeah, actually, we can do that. There are some challenges. Now, for example, piston ring, it will be like this. On the outer surface, it would be more easier to texture. But now, when you have a cylinder like this, so inside the surface, actually making it is a challenge. So we need to send the laser light here, and then we need to have to reflect it here, and then we need to do the texturing. So it is little more technically challenging, though it is possible. And if the size of the cylinder is bigger, it's more easier. But otherwise, we need to have some kind of an optics here, so where you should be able to move it, and also we need to control it, isn't it? So inside the cylinder, so that is a challenge. So outer surfaces actually we can do. Yeah, for rotary components, like what we do is we'll have a rotary precision rotary head here, then we have the laser here. So we keep rotating this. At the same time, with the control of the laser, we can move it as we require, and we can do the texturing. But now if it is inside the cylinder, so how do we do that? How do you take those optics, and also it should be reflected to these surfaces? So there are technical challenges there.
So then why can't we do it in the pistons?
Yeah, so piston hole surface, if you see, I have given you a picture in the beginning. See, basically the piston rings which make the full contact with the surface. So I think I just given the picture. Maybe if you see that, yeah, this I just gave it as an example, but here you can see, yeah, so this is the piston. It won't be like just like a cylinder. So theoretically, whenever we are studying IC engines, we draw a cylinder like this, and then we draw a piston like this, isn't it?
Yes,
Okay,
yes,
sorry. So we draw a piston like this, but piston shape is not just like this. And also if you see on this surface, there'll be a place where it will be like a curved
Yeah,
surface.
it will be
It's a complicated
scooped
surface.
only for mainly in diesel engines. There will be a cutting
Yeah.
also.
Yeah. So that's this surface mainly it makes the contact here.
Okay, so will the surface texture affects the burning combustion of the engines, like increasing the efficiency or decreasing?
Combustion, okay. I think I'm not sure about it, but it won't know how does it affect the combustion. So usually, uh, see, it also depends on the size of automation. So if you make it smaller, I think it'll be better efficiency. So nowadays we have automizers. I think I have not shown you that picture. So usually, whenever you are trying to push the oil into the cylinder chamber, so the fuel actually will come out through a micro holes, small holes. Okay. So then it gets atomized. That means it becomes like a spherical particle. And if the diameter of this hole is smaller, you get the smaller particle. So in that case, oxygen which will be surrounding the combustion actually will be more. But if these holes are larger and if the fuel particle is like a bigger one, so it won't burn full percent, and then maybe at the core it will remain like a fuel, and probably it will be scavenged, that will it will be thrown out. So thus it is not efficient. So that automation, so that means making that fuel into small particles when you are injecting into the chamber, combustion chamber is very, very important. And that is actually improved with the help of the micro machining technologies and even with the lasers. So we can make that holes very, very small. So that actually improves the combustion. But I don't think the surface texturing will improve the combustion process as it is. But it will help in decreasing the friction and the temperature which gets generated at the walls. So there is a mechanism actually. We have the cooling mechanism to cool the whole cylinder and take away the heat.
So one more question, sir. So in the surface textured area, the carbon deposit will be how, sir?
Carbon?
Carbon deposits on the surface textured areas.
Yeah, actually, we never actually expected that will happen. But when we saw those images, we could clearly see that. So, what could have happened is that when you are exposing that surface to the heat to make the textures, so the carbon actually melts and then it re-solidifies there. So thus whatever is even inside or in the surrounding area is actually coming to that place. So when you see the same image, we surprisingly found that. So it was not actually the intention, we didn't expect that phenomena, but actually it happened when we do that.
Okay, sir.
That is an interesting. So sometimes in research it is like that. So you expect something, but you'll have always surprises. So this is one of such kind of thing.
Okay, sir. Thank you, sir.
Yeah, you have one more question? Yes.
With the advent of metal 3D printing process like SLM, can we create textured surfaces directly during the 3D printing process itself? Is it a viable solution, sir?
Yeah. So that is actually always surfaces have been a challenge in 3D printed parts. So whenever we say what are the disadvantages of 3D printed parts, we say that the strength is not sufficient. And then second one, we say the surface finish is not good enough for practically using it directly. Okay. So we go for post processing of metal 3D printed parts. So that is a big topic. So where we do the secondary operations so that we make that surface useful for practical applications. So thus we get actually, so that is the reason I initially talked about the surfaces, no? So whenever we have either a machining process or even 3D printing, we get a kind of stochastic kind of a surfaces. So wherein it is a randomness is there. So it is not very systematic. But if we need to control to that precision to get a texture, so it is really challenging. See, here in all these cases, when we measure the surface finish, so we actually still have a good surface finish. And also before we making the textures, we won't take a crude surface. We actually machine the surface and then do the texturing on it. Okay. So I can't take a mild steel plate which is there in the workshop directly and then we won't do the texturing on it. So we machine those surfaces and see that the flatness is maintained and then it comes to a particular surface finish. Only after that we do the texturing. But in 3D printing, still we don't have that kind of a control. So if at all we need actually probably, so we can put something like now the surface will be like a very random kind of a surface. So if it is a metal 3D printing, we can, if it is done by a powder or even a wire, even powder also is possible. So on this surface, you put just one laser pulse here. So a surface, a particle gets melted and gets attached, and then you can put like this. But still, it will be a random process, and I don't think you'll be able to get a good surface finish with the texturing at one step by using 3D printing. So that will be a challenge. Okay, then yeah. Thank you.
Thank you, sir, for the session.